Today we're gonna discuss binary search. We're gonna use a different method to find an element in the list. Okay, just to recall, last week we also looked at the problem of searching for a particular element X in the list L. And the idea is that we do exhaustive search. That is, we examine all elements in the list one by one. That means we iterate all elements in the list L. And at each iteration, you check if the element is equal to X. If it is, then you just output true and then you break. At the end of the iteration, you have exhaust all the possibilities. You have exhaust all elements in the list. You have checked every single element in the list and none of them is equal to X, and hence you can safely output false. So in the worst case, we actually need to go through the entire list and make n comparisons. Comparisons here is to compare whether they are equal. Okay, so if we have 500 elements in the list, then you need to make 5 comparisons. You need to take each one of these 500 elements in the list and check whether it's equals to X. So the question is, can we do better? Now, when we talk about exhaustive search, one of the problems that we analyze is to find duplicate value, to check whether a value exists, occur more than once in the list. Now, we have analyzed two versions of how to check duplicates. Okay, and the first version requires us to check the list again and again, multiple times. And second versions allows us to check the list just once. However, the second versions require us to work on a sorted list where every element in the list is sorted in some order, either non-increasing or non-decreasing order. Okay, such sorted order allow us to use a structure or the pattern for which we can manipulate to extract the features that we want. So the idea is the same here. If we don't want to have to check every element in a list to find this element X here, we can also use the structure of a sorted list to help us to rule out certain possibilities. Okay, so just to give you an idea, say, suppose you are given a sorted list, okay, in non-decreasing order, and you want to find X, a particular value X in the list, okay? So the idea is that we can split this list into two sublists, L1 and L2 at the middle. Okay, so let's just look at an example. So I have this list here. This is my list, and it's a sorted list, okay? So this is a sorted list here. And if we just run length of L to retrieve the number of elements in L to find that it has 16 elements. So I'm going to split half in the middle. So I will take first 8 element. Okay, this will be my first half. This will be my sublist L1. So I split the list into two sublists L1. So the yellow highlighted part is L1. And then I have another second half of the list, we call it L2. Okay, so this is a sorted list. We split it half. This is L1 and this is L2. Okay, so the first element in L2 is called Y. So in our case of examples here, Y is equals to 22. Okay, suppose we're looking for X is equals to 4, for example. Okay, suppose X is 4 and we want to find X in this list here. Okay, so we compare X with Y. So this is my Y equals to 22, X is equals to 4. If X is less than Y, since 4 is less than 22, if X exists, it must not be in this sublist L2 here. It will have to be occur in the first half. Okay, so it must be in L1, right? So if our target element is less than the first element of the second half, then you know that none of these elements can be the target element. Okay, so if it exists, if the target element exists, it must be in the first half. Okay, now if X is greater or equals to Y, for example, if X is, say, 36. Okay, so if X is 36 and this is my Y, okay, 36 is greater than Y, 36 is greater than 22. So if 36 exists in this list, it will not occur in L1, rather it will occur in L2, the second half of the list. Okay, so it will occur in second half of the list. So these observations allow us to see that you actually, when you want to find an element X in a sorted list, okay, you just need to make comparison once, okay, with the first element of the second half of the list, okay, and then you know that the next search is either in the first sublist or the second half of the list, okay. Once you make a comparison, X with Y is either less than Y or greater or equals to Y, then the next search that you want to look for is either the first sublist or the second half of the list. Okay, so for example, let's look at it one example carefully. So let's L1 is equals to first half. Okay, the first half will be from 0 to, so this will be slicing the first half elements. All right, that is, you take elements starting from 0 all the way, but not include index 8. Okay, and let's print L1. This will be my first half. Okay, and then my second half will be here. Second half will be starting from index 8 all the way to the end. This is my second half of the list. All right, so together they form the whole list. All right, so let's take the first element of the second half of the list. The first element of the second half of the list will be this element at the 0 index of L2. Let's print Y. Okay, in this case it's 22. And if I'm looking for, say, 4, okay, I make the comparison between X and Y. Okay, in this case, X is less than Y. Okay, so if it exists, it has to be exist in the first half. Okay, so I don't have to check second half anymore because I know if it exists, it can only exist in the first half. So I don't have to check every element in the second half anymore. So if X, say, is equals to, say, 36, okay, so now X is greater than Y. Okay, so which means that if X exists, it must in the second half. That means I don't have to check every element in the first half. I can rule out these possibilities. I only have to check the second half. I only have to focus on the second half. Now, this observation is powerful. It tells us that at every single comparison here, when I make one comparison, I rule out half of the elements from, I don't have to check. Early on, when we do exhaustive search, we check every single element one by one. But now, because the list is sorted, when I make comparison with the first element at the second half, I can rule out either the first half or I can rule out the second half based on the result of the comparisons. Okay? So we only need to search in either L1 or L2, but not both after we make the first comparisons. So after we make the first comparisons, we only need to search in either the first half or the second half and not both of them. Okay? Now, both sublists, either is L1 or L2, they contain half of the elements of the original list. Okay? If using exhaustive enumerations on the sublist that contain X, we only need n/2 comparisons in the worst case, where n is the number of elements in the list. Okay? Make it easier to read. Okay, so if you look at the exhaustive search, all right, if you have n elements in the list, in the exhaustive search, we need to make n comparisons. Now here, if we are dealing with sorted list, okay, and we do the strategy where we take out the first element of the second half, and we examine whether X is greater than Y or less than Y, and then we rule out either the first half of the second half. Okay, then if we do exhaustive enumerations on either L1 or L2, depends on your comparisons, then we only need to make n/2 comparisons in the worst case. Okay, we only check half of the elements instead of checking all elements after we just make one comparison. Okay, so the idea is, can we make use of these comparisons again and again to rule out half of the remaining elements? So it turns out we can do that. Okay, so we apply the same binary search strategy to each of these sublists here. Okay, so the idea is the same. We take the middle element m. Okay, if x is equals to m, then we found it. Remember, x is the value that we want to find. If x is equals to m, then we found it, we output true, and then we break. Okay, but if x is less than the middle value, okay, then you search for x in the first half of the list of L. Okay, and if x greater than m, then you search for x in the second half of the list. All right, so we apply the same strategy again when we search. So, for example, say this is my list here. Okay, this is the middle value m, which is 22. Okay, and then we are looking for 33 here, and this list is sorted. So you're comparing between 33 and 22. 33 is bigger than 22. So if 33 exists, it must exist in the second half. So which means I don't have to check anything before that anymore. I only concentrate my search on the second half. So I already rule out all the previous elements. I only need to check this number of elements here. Okay, so again, I take the middle value. So I don't do exhaustive search. I don't check every single element here, but apply the same binary search strategy. The binary search strategy is that you take the middle and you make comparison, and then you rule out either the first half or the second half. So the same thing, I will take the middle value, say for this is the middle value, okay? And then again, I make comparison between 33 and 43. Now this time, 33 is less than 43, which means if it exists, all right, then it will exist in the first half. It won't be exist in the second half. We don't have to check this because all of these elements is greater than x. Okay, so we know for sure they are greater than x because this is a sorted list from lowest to highest. So if it exists, it must exist in the first half. So I can rule out the second half and only concentrate my search in the first half now. Okay, again, I don't check one by one. All right, rather I use the same binary search strategy. Binary search strategy say that you take the middle value, okay, and you make comparison with the target value. Now 33 is bigger than 29, which means if it exists, it has to exist in the second half. Okay, now in this case, I don't have to check the first half of the list. I only check the second half of the list, which contains only one element. Okay, now again, this element has contained only one element. The middle value is itself. Okay, once you're down to one element, you just have to compare whether this is equals to x. Now, since 32 is not equals to the target value, we can conclude that it doesn't exist. Okay, so we make basically 1, 2, 3, 4. We make 4 comparisons. Okay, we make 4 comparisons only and conclude that there exists no x in the list. Okay, we only make 4 comparisons and we already can conclude that there exists no x in the list. Okay, now if this is called binary search strategy, if you use the exhaustive search and strategy, we will have to make, okay, so using binary search strategy, we make 4 comparisons only and conclude that there exists no X in the list. Okay. And if you use the exhaustive search strategy, where we check each element in the list one by one after another, then we will need to make 16 comparisons. Okay, so compare between 4 comparisons and 16 comparisons. Obviously, binary search strategy is more efficient. So, however, note that binary search strategy only work if the list is sorted. Okay, it doesn't work when the list is not sorted. Okay, if the list is not sorted, all right, we lose this, we can't make the conclusion that we can rule out first half or second half. Okay, so for example, if you just give you some random list, all right, that is not sorted, for example, in this case, this list here is not sorted. Okay, and we can't just make an assumption that if you take the meter value, say if I'm looking for, say, 22, and this is the meter value, all right, and 22 is actually more than 4, we cannot say that we will have to just look at the second half. That's not true, because this list is not sorted. It might exist that 22 is in the first half. Okay, so binary search strategy only work if it's in a sorted list. Okay, so this is very important. Okay, so let's make the comparisons here. So at each iteration of the loop, the size of the space to be searched is cut in half. Okay, so if you can see here, at the beginning we have 16 elements, all right, and then we're down to 8 elements, and then we're down to 3 elements, and we're down to 1 element. Okay, so at every single iteration, our search space has been cut in half, right? So in the sorted list of 1 million elements, the exhaustive search will need to examine each of the 1 million elements. Okay, but the binary search, we need to examine how many elements. Okay, so let's look at this. Let's examine this one by one. Okay, so if you are given a sorted list of 16 elements, how many elements you need to examine? The search space at first iteration, iteration 1, you know, the search space is now reduced to 8 elements. Okay, so after you have 16, you reduce to 8, and after you make the second iteration, you cut it by half, at most 4 elements. Okay, and the third iterations, again, you cut it by half because you can rule out the first half or the second half, so you're down with 2 elements. At the fourth iteration, your search space is reduced to just 1 element. Okay, so the number of iterations needed to reach just 1 element is 4 iterations. So after 4 comparisons, after 4 iterations, you left with just 1 element. Okay, so in mathematics, the number of times we can keep divide n by 2 is the highest number e, such that 2 to the power e is less than equals to n. Okay, so in other words, e is equals to log of n, log 2 of n. Okay, so this is the mathematical terms of finding the highest power of 2 that is so that 2 to the power e is less than equals to n. It's called logarithmic base 2 of n. Okay, it's a number of times, it's the smallest number of times that you can divide n by 2. Okay, so now if you are given 1 million elements, if you use the same binary search strategy, how many elements that you need to examine, how many comparisons that you need to make. Okay, so after the first iterations, the search space now is reduced to 0.5 million. From 1 million, it's down to 0.5 million. And the second iteration, Now it's reduced to 0.25 million. You cut by half. All right, every iteration, you can rule out either the first half or the second half. You don't have to check either the first half, or you don't have to check the second half. So your search spaces keep reducing by half. So after the third iterations, now it's 0.125. And you further down, it's reduced to 0.125 divided by 2 millions elements, and so on. So at how many iterations, it will reduce to 1 element. So we're looking at it, look at how many times we can divide n by 2, and so that it's down to 1. So we can run, for example, import mat. Okay, so mat.log of 1 million. Okay, it says that after about at most 14 iterations, our search space will reduce to 1 element. Okay, so after at most 14 iterations, okay, and your search space will reduce to just 1 element. Okay, so after, say, so if you compare between 1 million and 14 iterations, so you will have 14 iterations. So 1 million, you have to examine 1 million for exhaustive search. For binary search, you only make 14 comparisons. You examine 14 elements. For each of these elements, you make comparisons and rule out half of them, half of the list, okay? And then after 14, at most 14 iterations, you're down to 1 element to make 1 last comparison to check whether this is equals to the target elements, okay? And if a list is not sorted, we cannot use binary search, as we have seen as an example, because at every single iteration, you cannot rule out either the first half or the second half when it is not sorted, okay? So when it's not sorted, we can't use binary search, okay? So let's implement this binary search, okay? How do we implement it? So the idea is already given. You take the middle element, you make comparisons. Based on the comparison, you can either rule out the first half or the second half. And we know that this is efficient because it allows us to rule out a lot of elements from having to make comparisons, okay? From 1 million to 14 is a drastic improvement in terms of the number of computational steps required. So binary search is very, very efficient. However, it requires that the list is sorted, okay? Now let's look at the implementation. How do we implement this binary search? What is the step-by-step instructions for finding X in sorted lists using binary search? Now the idea is always the same. You want to be able to extract the middle element, okay? So to find out the middle element, we need to keep track of which element is the middle element and which half that we want to search now. So we make use of the index. Index starts with 0. Okay, this is index 0, and the last index is index 15. So this is the least element. Index 0 has value 1. Index 15, the last element, has value 63. So we have 2 variables, start and end. Start represent the start of this element here. Okay, start represent the index start, and end represent the last index, which is 15. Okay, now as long as there is still an element in the list that its start is less than equals to end, let n be the middle index in the range from start to end. Okay, so as long as there is still an element from start in our search space, so start and end will indicate our search space. Okay, so start and end indicates the indices of search space, our search space, or the sublist to search. Okay, at the beginning we have the whole list. Okay, so we have start equals to 0 and equals to 15. Right, now as long as there is still an element in the list, that is when start is less than equals to n, you take the middle index In this case, the middle index is 8, okay? And you're going to check the element at the middle index, whether it's equals to x. If it's equals to x, you already found it, you can output true and break, okay? Otherwise, if the value at the middle index is less than x, that means whatever that you need to search for is bigger than the value of the middle value. So if it exists, it has to be in here. It has to be in the second half. That means you can move the start index to n plus 1. So this is my m. I can move my start index to n plus 1 here. Okay, so which means in my next iteration, I'm going to start searching from index 9 all the way to index 15. Okay, if on the other hand, the middle value is actually greater than x, that means whatever you want to search for, x is less than the middle value. And then you only need to concentrate your search in the first half. Okay, so start from 0 and then end will move to index 7. That is n minus 1. Okay, so this is my m. I don't need to check anything afterwards because my x is less than the middle value. So I have to move my end. Remember, n will represent the last index of the subsequent search sublist that you want to search. We'll move to index 7. So we'll only concentrate our search from index 0 to index 7. Okay, and then you repeat again from step 2. Okay, so as long as start is less than or equals to n, that means your list is not empty list. It's not empty list. Yes, then you continue to find the middle value, make comparisons, and then rule either the first half or the second half. Okay, so that's the idea of implementation of binary search. Okay, let's implement this. Suppose I have a list which is sorted. Okay, and this is my target element. This is my x is equals to 23. Okay, I start with the 0 index and with the last index. So this is my whole search space. Okay, and again, when I want to find something, all right, and I want to output is either true or false, I have a variable called has found target. I first initialize to false. When I find it, it will be changed to true. Okay, so as long as this time we're going to use a while loop, all right, it basically say as long as start is less than or equals to end. Okay, as long as start is less than or equals to end, that means there is still element in the list. Okay, then we take the middle index, like the middle index. So middle index. Okay, is equals to the start plus n divided by 2. Okay. So for example here, in my first iteration, start is equals to 0, n is equals to 15. This is my start index. I start at index 0. My last index is 15. All right. And start is less than or equals to n, so it's true. 0 is less than or equals to 15. So we have to check. That means there is still element in there. And we're going to check whether the middle, what is the middle index. In this case, the middle index is start plus n divided by 2. So 0 plus 15 divided by 2. Okay, so let's do 0 plus 15 divided by 2. And you see that this is 7.5, but index has to be an integer. Okay, so we do floor divisions. Okay, so we do floor divisions to get integer because index has to be integer. Okay. So now when we do floor division divided by 2, so if you check now, 0 plus 15, floor division by 2, you get 7. Okay. Floor division means that when you just do normal computation, normal divide, but you remove the decimal. Okay. Floor division means you remove decimal. Okay. So your middle index now is 7. Okay, and what is the value at index 7? So let's look at L7 is 17. Okay, so you go to index 0, 1, 2, 3, 4, 5, 6, 7, which is 17. So you have the middle value is equals to L middle index. Okay, and then you make comparisons. So the comparison is if middle value is actually equals to your target, then you already found it. So has found target is equals to true. Okay, and then you break. Once you found it, so you set it to true and then you break. That means you stop running any iterations. Okay, else if middle value is less than x, okay, if middle value is less than your target value, or should I say if x is more than, if x is less than middle value, for example, okay, so if x exists in the list, it must exist in the first half, okay, and if x exists, it must exist in the first half, okay, so which means I need to start from 0 all the way, but not include the middle value, okay, so in this case, for example, then my end will be equals to m minus 1, middle index minus 1. So I'm going to move my end index to middle index minus 1 because everything after that we don't have to check anymore. Okay, else. So else means when x is greater than middle value. When x is greater than the middle value, if x exists, then it must exist in the second half. Okay, if the target that I'm looking for is greater than the value in the middle, then if it exists, it has to be exist in the second half, which means I don't have to take care of the first half. I don't have to check them. I start to move my start index to middle index plus 1. So I need to only start checking from the middle index plus 1, the value after the middle value. Okay, and that's it. That's all our binary search algorithms. Okay, so in the end, you should, for example, print out the value has found target. Okay, it's run. So it says false. 33 didn't exist in this list here. Okay. Now, in the exams and in the quiz 12, you will be asked to fill this table here. Okay. So for each one of them, you're going to execute it by hand. All right. So we're going to do this by hand now. So this is the implementations that you have to do it by hand. So we're going to do this together just to, as a practice. Okay. So let's do this by hand one by one as a practice. Okay, so let's start with first start is equal to 0, n equals to 15. Start is less than equals to n, so this is true. And my middle index will be start plus n divided by 2. Okay, so 0 plus 15 divided by 2. And we remove the decimal, you get 7. Okay, and we take the middle value, which is the value at index 7, which is 17. Okay, now we go to the next iteration. So this is middle value here. Okay, and then you go to line 9 and then you compare between middle value and x. So 17, is it equals to 33? Since 17 is not equals to 33, this is false. It will not execute this. Then it will go to line 12 and check if x is less than middle value. So x is 33, middle value is 17. So you are checking whether 33 is less than 17. This is not true. 33 is not less than 17. So you don't execute line 4. Rather, you go to line 15. Line 15 say that you will execute line 17 because this is the else statement. So line 17 say that now the value of start is equals to the middle index plus 1. So my value of start here will be the middle index, which is 7 plus 1. So now my start will be equals to 8. Now in my second iteration, n stay the same. It will be from index 8 all the way to index 15. Now if start is less than equals to 15, now this is true. Okay, so now what is the middle index? Given start is equals to 8 and equals to 15, what is the middle index? So again, the middle index equals to start plus n, floor divided by 2. So you do your own calculation, 8 plus 15. So we have 8 plus 15, all right? And then you floor division by 2. So 8 plus 15 is 23, and you want to divide by 2, and you want to take the floor division. This will give you 11. Okay, so you put 11. So when you do the calculations, you do the calculation manually, 23 divided by 2, which is 11.5, and then you remove the decimals to get 11. And then you need to find what is the middle value, which is L of middle index. So middle index now is 11. So you go to your list L and look for index 11. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which is 32. Okay, so now your middle value is 32. Okay, this is 17. Okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Now we go to line 9. Okay. We check whether the middle value is equal to x in our, since x is equal to 33, our middle value is 32, they are not equal. So you go to else if statement to check whether x is less than middle value. 33 is not less than the middle value, it's greater. So we execute the else statement and we make start now is equals to the middle index plus 1. So now start is equals to the middle index, which is 11 plus 1. So it's 12. And again, stay the same. And start is less than equals to n. So this is true. And now what is the middle index? The middle index will be 12 plus 15. So 12 plus 15 will be 27. And you do a manual calculation. 27 divided by 2 is 13. Remove the decimal. And then you look for the middle value, which is L of 13. So you look for L of 13, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, which is number 4, which is 44. Okay. Now, and then you check whether the middle value is equal to x. It is not equal to x. Then x is less than the middle value. X is 33. 33 is less than 44. So it is true. Then you move n to middle index minus 1. Okay, so now my n is the middle index, which is 13 minus 1, which is 12. Start stay the same. And since start is less than equals to n, this is true. And what is the middle index? So 12 plus 12 divided by 2 is 12. Okay, the middle index is start plus n divided by 2, remove the decimal. So what is the value at index 12? Okay, so the value at index 12 would be 29. Okay, oh, sorry, will be 43 actually. Will be 43. Okay. Okay, middle value is 43. Is it equal to x? It's not. So you go to else statement. Is 33 less than 43? Is true. The target value is less than 43. So I'm going to execute line 14. Say n is now equal to middle index minus 1. So middle index is 12. And minus 1, so it's 11. Okay. N is equal to middle index minus 1. So 12 minus 1 is 11. And start stay the same, which is 12. Now, start is 12, n is 11. start less than equals to n will be false. Okay, so once it is false, start less than equals to n is false, you stop. All right, because this is a while statement. As long as start is less than equals to n, you're gonna run line 7 to line 17. However, at this point, after at iteration, at the last iteration, start is not less than equals to n, it's false, so we stop. And this is where we print that it has not found target. Okay. And you can try with different value of x, for example. Say now x equals to 32. Okay. So when you run it, it says it's true. And you can print out the intermediate value to check. Okay. Say print middle index, middle value. Okay. And you also have to print start and end. Okay, so let's do this. So say start is 0, end is 15. Your middle index is 7, and your middle value is 17. Now 17 is the middle value, and x is 33. So x is not less than middle value, so it will execute this statement here. We say that start is equal to middle index plus 1. So now your start will be the middle index, which is 7 plus 1, 8. Now 8 plus 15, 8 is the start and n is the 15. All right, and what is the middle index? So the middle index will be 8 plus 15, which is 23, divided by 2, remove the decimal, you get 11. So the value at index 11, which is 32, and since this is equal to the target value, you already break. And output, once you break, once you execute line 12, which is break, you will end all the iterations, and you go to line 20 to print that it has found target, which is true. Okay. So here is the example. You can be more precise. For example, start is this. Okay. And then n is this. And middle index is this. Then middle value is this. And it will tell you what are these values for if you want to look at the intermediate steps. Okay. So in the exams and in the quiz, you are asked to fill out this table yourself. So you have to go through these executions one by one, performing binary search on the list to search for a target element. So you need to fill out what is the start value, what is the end value, is start is less than equals to n, what would be the middle index, and what is the middle value. And is there a next iteration? If there is, what is the start? What is the end? Is it less than equals to end? If start is less than equals to end, what is the middle index? What is the middle value? Okay. And that's all for today. And before we leave, actually, I need to a very quick recap or summary comparison between exhaustive search and binary search. Both methods perform a search over a search space. Okay. For linear search or exhaustive search, you'll find an element in the list by searching the elements sequentially, one after another, until the element is found in the list, or until at the end of the list, you didn't find any, you exhaust the list, and conclude such element doesn't exist. Is in the list. Okay. And for binary search, we didn't check every element one by one. Instead, we look at the middle element, okay, and we make comparison between this middle element with the target element. Based on these comparisons, we can rule out either the first half or the second half. And then we apply the same binary strategy. That is, whatever either it's the first half or the second half that you're looking for, you apply the same binary search strategy. You also extract the middle element, say in the second half, and make comparison again. Based on the comparison, suppose you only need to search for the first half, then you take the middle elements of the first half and make comparison again. And this idea of applying the same strategy in each of these sublists here is called recursive. That means you apply the same binary search strategy in each of these sublists, okay, recursively, okay, until the middle element is matched with a search element, or again, you exhaust, you can, or you left with no element or just one element. And conclude no elements in the sublist, and conclude that no such element exists. No such element in the list. Okay, so that's the difference between the linear search and binary search, but also very important to know that binary search only works in sorted list. If the list is not sorted, if you use this implementation on a list that is not sorted, you won't get the right results. Okay, I'm going to make a big remark here. Okay, sorting. So if the list is not sorted, okay, binary search will not work, will not give the right result. Okay, so if you want if you want to use binary search because it's efficient, it only takes very minimal amount of comparisons, and then you have to sort these first. So if you want to use binary search, okay, you will have to sort the list first. Okay, so as we have discussed informally in the previous lecture, sorting a list is very computationally expensive. So it requires, in the worst case, say n log base 2n computational steps, roughly. Okay. Where n is the number of elements in the list. Okay, so if you have a large list, you actually incur this number of cores, computational cores. Okay, but however, if you have to search the list many times, okay, it is worth to sort the list once. Okay, because once the list is sorted, it will stay sorted. All right, and if you want to search multiple values, say x equals to 32, x equals to 33, and then it's worth it to actually sort the list once and incur this cost. Okay, but subsequent search and perform binary search using which is more efficient. Okay, so if you have to search a list many times, it's worthwhile to sort the list once by running this computational step here to sort the list once, and then when you do the search, if you want to search for say 32, 33, 43, you want to do multiple such search, then using binary search on the sorted list will be very efficient. Okay, so that's the end for today. Thank you, class.